Okay, so second law of thermodynamics, in order for a process to be spontaneous, the delta S of the universe has to increase, and we can cut the universe into two parts, the system and the surroundings. And so why that's convenient is because, again, the universe is a big place, right? So when you're carrying out a reaction in like a beaker, let's say, you're going to define that reaction in that beaker to be your system, and then everything else counts as the surroundings. Okay, so first what we're going to do is take a look at the system portion of things and see if we can't predict whether or not these processes are going to be spontaneous or non-spontaneous, or rather, I lied. Not spontaneous. We're going to build up to that point yet of looking at the universe. We're going to see whether these processes are entropically favorable or unfavorable. Okay, so, and then we're going to kind of keep a list of the things that would make something entropically favorable. Okay. Okay, so I'm just going to put down some chemical processes, and we're going to determine whether or not we think that they are entropically favorable. And remember, with regard to entropy, what you want to keep in your mind is this idea that entropy is the energy of disorder. We kind of had this more wonky formal definition, but as I said, it's much harder to wrap your head around that definition until you get a little bit further in your chemistry career. So what you want to think about is, are these processes creating more order or disorder, right? Things that are creating more disorder are going to be entropically favorable. Okay, so let's say if we took H2O liquid, converting it to a gas. Or okay, so take a minute and see if you can't determine whether these processes are entropically favorable or unfavorable. And for this first one here, we're going to make it an iClicker question. So you'll enter A if you think it's favorable, or B if you think it's unfavorable. All right, and again, what you want to ask yourself is, if going from a liquid to a gas, does that create a more disordered state or a more ordered state? If it's a more disordered state, that would be considered something entropically favorable. If it's a more ordered state, then it's entropically unfavorable. All right, so going from a liquid to a gas is indeed something that's entropically favorable. Gases are the most disordered state of matter that you could possibly have, right? So if we want to go back to our entropy diagram for water as it changes in temperature, what we saw was that if we go from the solid phase to the liquid phase, there's a big jump in entropy. But if we go from the liquid phase to the gas phase, that jump is even greater. right? Gas molecules, they have absolutely no set orientation. They completely fill whatever sort of vessel they're in. They just go about crashing, ping-ponging about within that vessel. They are about as disordered of a substance as you could possibly have. So anything that creates a gas is entropically favorable. Entropically, meaning pertaining to the entropy of the system, favorable. And so then on the flip side, if you're going from a liquid to a solid, this is creating a more ordered state, right? Solids are incredibly ordered. If we just took this ammonia, for example, the ammonia molecules will be sort of fixed in position in the solid. Their neighbors are going to be constant. Their orientation is set by that solid. They really are doing nothing but kind of just like wiggling around in place. So this would be an entropically unfavorable event. Okay, so sort of keeping a list here. Gases, more entropically favorable than liquids, more than solids, right? So that state of matter is going to influence the entropic favorability of a process. Okay, so now let's take a look at two new things here. All right, so in the first one, we have another phase change going from, I don't know if it's a phase change exactly, but changing the state of matter, dissolving solid sodium chloride into solution, creating an aqueous product here, right? Remember that AQ means it's aqueous. So that's when you take solid sodium chloride and dissolve it into water. Is this going to be entropically favorable or unfavorable? Again, we just want to ask ourselves, does this process create more order or disorder? In this case, we're going from a solid, which is highly ordered, to an aqueous solution. And so let's just remember microscopically what an aqueous solution looks like, right? When we dissolve sodium chloride into water, those sodium ions and those chloride ions dissociate and they begin to float around freely in that solution in this very disordered state compared to that very orderly solid. And so that's why this process will increase entropy or be entropically favorable. All right, so now I want you guys to take a look. The next example here is actually a chemical reaction. This is what's called a precipitation reaction, where you mix two aqueous solutions together, and one of your products is aqueous, but the other is, whoops. Uh-oh, I lost my place. But the other is a solid. Okay. There you go. This little button messed me up. So we want to determine whether or not we think that this reaction will be entropically favorable or unfavorable. So again, we'll do an eye clicker with this one. If you think it's favorable, it's A. If you think it's unfavorable, it's B. Sorry, I think I was muted if somebody was trying to say something. All right, awesome. Seems like for the most part, we're getting the name of the game here, right? So both of these reactants are aqueous solutions. So those are relatively disordered states. And then I create one aqueous product, but also one highly ordered solid product. All right, so this would be an example of a reaction that's entropically unfavorable. Now, this reaction actually does occur spontaneously. Okay, so if you remember, our whole goal was to create this chemical potential, which contains both a we have this chemical potential here. And this is going to help us predict whether or not a reaction is spontaneous. And it has these two components, enthalpy and entropy. Right now, we're just looking at the entropy component. We haven't quite gotten to the point where we built our chemical potential yet. And so we're getting there to whether or not it happens. Right now, we're just looking at the entropy factor. And so even though that reaction right here does occur spontaneously, it is not an entropically favorable reaction. Okay. So again, to update our little list here, we can say that aqueous is better than solids. Okay, so now let's take a look at a few more chemical reactions. Let's actually do. And for the last one. All right, so we got 3 chemical reactions here. And again, our goal is to determine whether they are entropically favorable or unfavorable. All right, in this first reaction here, we go from a ordered solid to a solid, but also a gas here, right? So this is a reaction that converts a solid to a gas. That is an entropically favorable reaction. All right, again, there's nothing more disordered than a gas. So now let's look at the next reaction. This reaction is what's called a combustion reaction, where you take this hydrocarbon right here, you react it with oxygen gas, and you get carbon dioxide gas and water vapor. Okay, so now this one's a little bit more tricky because you have a gas that's being consumed, but you also have gases that are being produced. So I want everybody to take a minute. We'll do an eye clicker again, see if you think this is going to be entropically favorable or unfavorable. Okay, so at this point, it's just a numbers game, right? How many gas molecules are being consumed in this reaction? Well, it's 11 O2s being consumed per mole or, per molecule of fuel. But you're going to get a total of 15 gas molecules on the product side, right? So in this case, because you consume gas and create gas, you're going to have to look at exactly how many gas particles are being consumed and produced. And since you have more gas particles on your product side, this is an example of an entropically favorable reaction. Right? So the more particles created, the more entropy. So then with that principle in mind, I want you guys to do this third one for me. Again, we'll do it as a clicker question. Take a second and tell me whether this reaction down here is going to be entropically favorable or unfavorable. All right, awesome. For most part, it seems like we're understanding here. I go from having 4 gas molecules on my reactant side to only 2 on my product side. So this is entropically unfavorable. I'm consuming more gas molecules than I'm producing. So I'm getting less particles, right? More particles would be more entropically favorable. Okay, so then the next thing we're going to do is we're going to go back to that entropy diagram for water. And of course, what we said that this illustrates is, again, going from solid to liquid. There's this huge jump in entropy. And then going from liquid to gas, there's also this huge jump in entropy, right? And just to note, on the x-axis here is increasing temperature. So now let's just kind of zoom into one region here, right? So not talking about a phase change, but let's say that our phase is constant. And I'm going to look at what happens to the entropy as my temperature increases. We can see that as the temperature increases, there's an increase in the entropy as well. Okay, so that's one of the things we're going to update our list with, is that if we increase temperature, it will increase the entropy of the system. And in order to sort of understand why that is, let's just remember temperature is proportional to the kinetic energy of the particles in that sample, right? So roughly speaking, temperature is just a measure of how quickly molecules are moving around. And so the more quickly molecules are moving around, the more they're going to be crashing into one another, the more they're just going to be creating this sort of disorderly fashion, right? So again, increasing temperature just by virtue of increasing kinetic energy will increase the entropy of a system. All right. One of the ones that's, I think, a little bit harder to see because it's more closely tied to our sort of wonky example is that another thing that will increase entropy is increasing the volume. Right? So if we imagine we have this sample of gas and we increase the volume of that gas, there's just more places for those gas molecules to go. If you remember, our wonky definition had to do with the number of our wonky definition of entropy, this kind of formal statistical mechanics definition, was that the things would increase in entropy if they had more chemically equivalent ways to arrange themselves. So just by increasing the space in a container, there's just more XYZ coordinates for those molecules to put themselves in, right? So there's more ways for them to arrange themselves. And one that's really hard to see, and you're just going to have to trust me on it until you get to sort of upper levels of of just in general chemistry, is that it also increases with increased atomic size. And that's a pretty minor factor in all things considered, if I'm just in general, but if I'm going to compare a sample of helium with, say, radon, because radon is so much larger of an atom, it has more energy levels that it can sort of distribute that energy over. And again, this is just something that it's not quite clear why that is, so you're just going to trust me on it. But it again goes to our very formal definition and this idea that there are more energy states for radon to distribute itself over than helium, which is very tiny. Okay. And so then the last one, we're going to compare two molecules and try to ask ourselves which one we think has more entropy. Carbon dioxide, or what's called propane, C3H8. And I'm going to draw out the Lewis structures here. All right, and so this is a really tough one, but I'm just curious to see how y'all do. So again, we're going to sort of do an eye clicker thing, A or B. You're going to tell me which molecule you think has more entropy. They're both gases, by the way. I don't know if that's going to change anybody's mind, but both carbon dioxide and propane are gases. So in terms of the state of matter, it's a wash. All right, so again, this was a tough one, but it's actually B. And that's just because of, again, there's more energy states, and really how you can sort of think about it is there's more ways that you can kind of kink this molecule, more conformations available to a molecule that has more bonds. If you think of just, when you played with these model kits in lab, right? If you built a model kit of carbon dioxide, it's kind of just like a brick. It doesn't really move around at all because there's only those two bonds. Where if you built this thing, it would be kind of big and floppy. You could twist it around in multiple different conformations. So because it has more bonds, it has more rotational states and is thus a higher entropy molecule. All right, so we made a list of these things that for a system, right, for what's in our beaker, make it entropically favorable. There is a hierarchy here, right? So number of bonds is like the least important factor whereas the state of matter is by far the most important factor, right? So there's sort of this hierarchy of importance to these various things that we've talked about, importance, in terms of considering whether a process is entropically favorable or unfavorable. Okay, so now we're going to, again, go back to this equation. So we talked about a bunch of things for our delta S system that made it favorable, right? And again, the whole idea is that in order for it to occur, the delta S of the universe has to be greater than 0. So now let's take a look at a process. So for example, liquid going to a solid. This is something that we know to be entropically unfavorable, right? I'm creating more order, which is bad from an entropy standpoint. So that means that the delta S of the system is going to be negative. It's going to be less than 0. Okay, that's what it, right? Entropy would be positive if it's disorder. It's going to be negative if it creates order. But we also know that this is a spontaneous process, right? So how does that work? If my delta, this term right here is negative, how could it be possible that the delta S of the universe is still positive? Well, we got this other term over here, the delta S of the surroundings. And so if the delta S of the system is going to be negative, that's fine as long as the delta S of the surroundings is a large positive value. Then it can overcome the negative effects of the system and result in a still positive entropy of the universe. Okay, and so how does that work? Well, it works because these processes that are entropically unfavorable, they're always going to be exothermic, right? And so liquid freezing into a solid is an exothermic process. There is heat being lost by that liquid to the surroundings in, your freezer where you put it in there, right? So in order for delta S of the universe to be greater than 0, that means that the delta S of the surroundings is larger than the delta S of the system, specifically the absolute value of it, right? Because the system's going to be negative. Okay, so those are the only conditions in which this would be spontaneous. Okay, and so these exothermic processes, despite being entropically unfavorable, they can still occur as long as the delta S of the surroundings is greater than that of the system, of the contribution to the system. And it turns out that the delta S of the surroundings is equal to the heat lost by the system divided by temperature. Right? So the way that you're creating more disorder in the surroundings is by releasing heat to the surroundings, right? So when that ice, that water in that ice tray is freezing, it's losing heat to the molecules around it in the freezer and is increasing the disorder in those molecules, which is why the universe allows it to create more order in the system. Okay, as long as there's a net increase in entropy of the universe, it's allowed. All right, so now we're going to take this and plug it back into our equation up here. Okay, so now we get that the delta S of the universe is equal to the delta S of the system minus the delta H of the system divided by temperature. And we like this right here because now it defines everything in terms of the system, things that are easily measured, right? It's hard to measure everything that's happening in all of your surroundings. It's easy to measure whether or not heat is coming or going from your system, right? So we like this here because now all of those terms are in terms of the system. All right, and then lastly, the entropy is measured in joules per Kelvin. And in order to get a chemical potential, we got to be in joules. So what we're going to do is take everything here and multiply it by negative T. And so what we get is negative T is delta S of the universe equal to the delta H of the system minus T delta S of the system. And so now we have what we're going to call our chemical potential. This is delta G. Delta G equals the change in enthalpy minus temperature times the change in entropy. This is what we've been working to build, our chemical potential formula here. Okay, and the delta G is just this negative T times the delta S of the universe. And remember, we said that in order for a process to be spontaneous, that meant that the delta S of the universe was greater than 0. And since delta G equals negative T times delta S of the universe, that means that the delta G must be negative in order for a process to be spontaneous, right? And that was our goal, was to build this chemical potential such that we could predict whether or not these chemical processes were spontaneous or non-spontaneous. Now we have our chemical potential, our delta G, and as long as the delta G is less than 0, we can conclude that that process is indeed spontaneous. All right, so now we're going to take that formula and we're going to start thinking about the different values that delta H and delta S could be. So here's my formula. Okay, and what I want to do is I want to build this table where I say, all right, for a given sign of my enthalpy and entropy, what is going to be the sign for delta G? Oops. Right, so what do I mean by that? I mean, let's say that I have a negative delta H, what we call an exothermic process, and a positive delta S, something that's entropically favorable. What is going to be the sign of delta G? All right, so we'll do another eye clicker here. You're going to say A if you think delta G is going to be positive, or B if you think delta G is going to be negative under the conditions where delta H is exothermic and delta S is positive. It's entropically favorable. All right. And one thing to note is because we're in the world of thermodynamics, T has to be in Kelvin, which is always a positive number. You can't have a negative temperature if your temperature is being measured in Kelvin. Okay, so what I'm going to do is I'm going to split this up into these two parts. Okay, so delta H minus T delta S. just going to move this over and add this plus sign here, right? So delta H plus negative T delta S. Look at those two terms individually. So for the delta H, I'm going to plug in a negative value. And then I'm going to be adding negative T times delta S. If delta S is positive, that means negative T times delta S is going to be negative. And a negative plus a negative is negative, right? So in this case, under these conditions, delta G will be negative, or we say spontaneous, right? Because that was our conditions for spontaneity. And this will be true at all temperatures. All right. So now we're going to look at another situation where we have an endothermic reaction and an entropically unfavorable process. And again, we want to ask ourselves, what's going to be the sign of delta G? So again, you're going to say A, it's positive, or B, it's negative. Again, think about how we just established it for the previous example, right? Think about the signs of these two terms and what they're going to mean for the overall sign of delta G. All right, so nice. So delta G will be positive in this situation, right? Because I'm going to punch in a positive number for delta H. And I'm going to then, if it's negative T times a negative number, that will again be a positive. And adding a positive with a negative is going to be positive, right? So then I have delta G. This will be non-spontaneous at all temperatures. All right. So now let's look at a reaction that's exothermic, but entropically unfavorable. And let's think about what the sign of delta H would be. Okay, so for here, again, my delta H is negative. But now my other term is going to be positive, right? So they're kind of dueling here. I got my enthalpy saying it should happen, but my entropy saying it shouldn't happen. And so in this case, it's really going to matter what the relative size of these two terms are here. Now, one thing to note is that this one is not just delta S, but delta S times negative T, right? So the magnitude of this term right here is going to be dependent on the temperature. So what do I mean by that? Well, let's just think of a very simple example. Let's say that we're at 0 degrees Kelvin. Let's plug in a 0 for that temperature. Is this going to be entropically favorable or unfavorable? Well, if this term isn't here, then delta G will be negative because my delta H is negative, right? So at low temperatures, this term right here, the T delta S is very small, negative T delta S, right? So at low temperatures, this is a very little positive value. And so it's going to be entropically favorable at low temperatures, or I'm sorry, it's going to be spontaneous at low temperatures. But if I'm at high temperatures, now all of a sudden that T delta S is a very big number. So at high temps, all of a sudden this is a very big positive number. And that means that delta G is positive. So at high temperatures, this would be unfavorable or non-spontaneous. Okay, and then our last situation here, sort of the flip side of what we just saw. Now we're going to take an endothermic reaction, but one that is entropically favorable. And now we're going to see sort of the exact opposite of what we saw before, right? Now the enthalpy is saying that this shouldn't happen. It's positive. But my entropy is saying that it should happen because delta S is positive, which means that this term right here will be negative. So again, it's going to depend on the relative size of those two terms. At low temperatures, this T delta S is very small. So the positive delta H is going to win out. So this will be non-spontaneous at low temperatures. But if I then crank up the temperature and I go to high temperatures, all of a sudden that second term, that entropy term, becomes much more important, becomes much larger. And so this will be spontaneous at high temperatures. All right, and just to sort of think about it, we talked about reactions or really phase changes that were exothermic, but entropically unfavorable, right? So remember that this would correspond to, well, actually, I want you guys to tell me here. I'm going to put two phase changes down, going from H2O, or rather, let's just say, so going from melting, going from a solid to a liquid versus freezing, going from a liquid to a solid, which one is going to fall under this category here of being exothermic but entropically unfavorable? All right, so we'll do a short answer here. Freezing or melting, which one is exothermic but entropically unfavorable? All right, so again, H2O liquid to H2O solid. This was what we call freezing. Or H2O solid to H2O liquid. This is what we call melting. And we want to know which one falls into the category of being exothermic but entropically unfavorable. Well, entropically unfavorable, that would be the one that creates more order, right? Not only that, but freezing, in order to get to that solid phase, the liquid has to get rid of a bunch of heat. So that would be an exothermic reaction or process. And so an example of this category here would indeed be freezing. And that should make sense because we know that freezing is spontaneous at low temperatures, right? That's when water will freeze, is when it's at low temperatures. But we don't just have the ocean turning into ice because it's non-spontaneous at high temperatures. And on the flip side, melting would be an example of a process that is endothermic, but is entropically favorable, right? We're creating more disorder. And that should make sense because this is melting is something that doesn't occur at low temperatures, but does occur spontaneously at high temperatures. All right, so this is sort of this cheat sheet chart that we made. Let me get rid of this portion right here, right? Based on the value of delta H and delta S, we can predict what delta G will be as well.